Hey guys, it's Rena, and today we're going to be doing lesson 2.2, but today's special guest is...
Hi, I'm Alicia.
Okay.
So first, we're just going to start off with some notes, and we're going to start with the difference between linear and arithmetic sequences. So a normal slope-intercept form of a linear function, that's going to be b plus mx, and the initial value is a0, or in this case, b. The difference is with arithmetic functions or sequences, the d is going to be the constant rate of change. So the d is basically the same as the x in a linear function. So for point slope form, the normal equation is y1 plus m times x minus x1, or y minus y1 is equal to m times x minus x1. So the two are similar because when you have your point slope form, it's the same. This equation is going to be the same as the arithmetic sequence. So the y1 is going to be the ak, or like whatever nth term that you have, and then the m is going to be the d, and the two x's are going to be the n and the k. So next is going to be exponential functions versus geometric sequences. So a normal exponential function is a b to the power of x. And in this case, in relation to geometric sequences, the b is going to be the r in this case. So these are just the same. The g of o is going to represent your a, or like the initial term, if you can read that, and the r is going to represent the b, and then the n is going to represent your x, or whatever you're putting to the power, or the exponent. So the shifted exponential function is y1 r x minus x1, and that's going to be related because, once again, the y1 is going to represent the gk, or the nth term that you're using, and then the r is going to represent your r, and the x minus x1 is going to represent your n minus k. So the difference between domains and like domain sequences between regular exponential functions and geometric functions or sequences is that geometric sequences have discrete points. So what that means, let me fill this in really quick. So what that means is the geometric sequence is only going to have specific numbers. However, on a normal exponential function, it can represent all real numbers that are related to the function. Yeah. All real numbers. And once again, discrete just means individual, separated coordinate points. So linear functions and exponential functions can both be expressed analytically in terms of an initial value and a constant involved with change. There is a difference between the two, though. Linear functions are based on addition and exponential functions are based on multiplication. So, over equal input intervals, if the output values of a function change at a constant rate, then the function is linear, so that's mainly focused on adding. And if the function or the output of values change proportionately, then the function is exponential, and that will be multiplying the ratio. A function has a following coordinate points. Could the function represent a linear function, exponential function, or neither? So when you're looking at this, if the input values have a constant change, so these are constantly changing by 1 for all of them. Well, this one's changing by 2, but it's still constant. Then we are going to have to look at the output values and how they change. So this is changing by a multiple of 4. So because it's multiplying, that means that the output values are changing proportionately. So this is going to be exponential. The next one, the output values are changing by +4 and +3. So that's going to be neither, because it's not changing at a constant rate. So it can't be linear, but it's also not being multiplied, so it can't be proportionately. And then the next one, it's adding by 2. For the input intervals. And then the y values are adding by 8. If you can see that. So the last function is going to be linear. So next we're going to make the point slope form equation, and we're going to convert that into the arithmetic sequence equation that we saw earlier in the notes. So first we have to find the slope between the 2 points 3, 7 and 8, 1. So first we have to find the slope. So m, oh my goodness, that m, y2 minus y1 over x2 minus x1. So first, our x1, or I guess I'll start with the y's, our y1, or our y2 is 1, and then our y1 is 7, and then our x2 is 8, and our x1 is 3. So that's going to equal -7 over 5, which is going to give us our slope. Or in this case, our m. Oh, wait, it's over there. Same thing. Okay, so now we're going to write the point slope form equation. So it's going to be y minus 1 is equal to the slope -6 over 5 times x minus 8. And in order to convert it to the arithmetic sequence, we have to add this y from over here to the other side. So the final equation is going to be y equals -6 over 5 times x minus 8 plus 1. So that's for the arithmetic sequence.
Hey guys, it's Rita, and I'll be picking up where Annalisa left off. So for number 5, it is known that f of x is an exponential function and that it passes through the points 2, 5, and 4, 12. Write an equation for this function. So the hardest part about this one will just be finding the ratio, because it's exponential and it's kind of hard to tell just based off of looking at these two coordinates. But we just have to be reminded of our last lesson where we found that y equals ab to the power of x, or in other words, y equals a times our ratio to the power of x, where a is just our initial value. So here you see that our x value drops from 2 to 4. So if we're like going by this formula, 5 times 5 is our initial value, by the way, from here, times our ratio, then, which we don't know yet, then we would only be at 3 something y value, but we want to get to 412, so we'd have to multiply by our ratio again. So again, our initial value, which is 5, from right here, times our ratio would only get us to the coordinate 3 something, but we have to get to 4 something, but we know it's 12. So we have to multiply by our ratio once more, and that would equal 12, because that is our y value at 4. So now you can solve for r. 12 equals 5r squared. Sorry, you can't see the very well. So then you can divide by 5 on both sides. 12 over 5 equals r squared. Then to get that square out, you can just square root both sides. So our ratio would be the square root of 12 over 5. So now going back to our formula over here, we know that y equals our initial value, which is 5, times the square root of 12 over 5 to the power of x minus 2. Now you could also write this as y equals 12 times the square root of 12 over 5 to the power of x minus 4. It just depends on which coordinate you want to, which coordinate you want to focus on. Just make sure that it matches on both sides. Like make sure you don't have y equals 12 to the power, or times square root of 12 over 5 to the power of x minus 2. It has to be x minus 4 since that's the x coordinate. But either of these equations would be correct. Okay, now these ones are pretty self-explanatory, but we're just identifying the constant. So if it's a slope or ratio, depending on if it's linear or exponential. And yeah, so y equals 4 times 2 to the power of x. Here we can tell it's an exponential function, so it's just a ratio of 2. And then for number 7, y equals 5x plus 7. It's linear, so it's just a slope of 5. The following functions are either linear or exponential. Which is it? Justify your answer. So here we can see that x is jumping plus 4, and then plus 4 again. And here it's decreasing by 4 and decreasing by 4 again. So the change in x is constant, or it's proportional. So then we can look at the y, and it's linear there. You can see that it's changing by the same amount each time. So you know that it's linear. Constant slope of -4. And then here for number 9, our x is proportional because it's jumping by 2 each time. And it looks like we have a ratio of 3 because we're multiplying by 3 each time. So it's exponential with a ratio of 3. So here we're just looking at some points and deciding whether they're linear or exponential or neither. So here let's first check the x values for number 1. It goes from 1 to 2 to 3, which is proportional. It's jumping by 1 each time. Then from 2 to 8, first we can think of this linearly. So from 2 to 8 you're adding 6, but then from 8 to 20 you're not adding 6. So we already know linear's out of the question. Then from 2 to 8 you're multiplying by 4. Then from 8 to 20 there's no correlation there either, so we know it's neither. We can just leave it at that. For number 2, x's are proportional, 10 to 11, 11 to 12, jumping by 1. Then from 30 to 20, we are subtracting 10. And from 20 to 10, we're also subtracting 10, so we know it's linear. Then for number 3, 13, 14, 15, x's are proportional. Then y, we're going from 20 to 4, and then 4 to 4/5. So right off the bat, we can tell it's not linear, but we know that from 20 to 4, you're dividing by 5, or you can say you're multiplying by 1/5. And then from 4 to 4/5, you're also multiplying by 1/5. So we can see that it's exponential. And for number 4, our x's are proportional. 6 to 12, you could say it's multiplied by 2 and say, oh, it's exponential, but then 12 times 2 isn't 20, so we know it's not exponential. From 6 to 12, you're adding 6, and then from 12 to 20, you're adding 8, so it's neither. I thought we were going somewhere there, but clearly not. Okay, now we've already done a few questions like this, but I'll go over just a few more of them. Following functions are either linear or exponential, which is it? Justify your answer. So for number 6, for instance, you can tell that from 4 to -2, you're adding 2, and from 2 to 0, you're adding 2 again. So the x's are proportional. So now we can look at the y's. You're subtracting 4 each time. So here we know that it's linear, because for every input change of 2, f of x has a constant change, or a constant rate of change of -4. Okay, now for this problem, we can see that x is changing proportionally. From 11 to 20, you're adding 9. Then from 20 to 29, you're adding again. So now you can check your y. Here you can either say that you're dividing by 2 or multiplying by 1/2. From 4 to 2, you're also multiplying by 1/2. So here we can say that it's exponential, because for each input change of 9, f of x changes proportionally by a ratio of 1/2. Okay, now here again we're just identifying whether it's linear or exponential, and the constant, so the slope ratio. So here we can tell it's exponential from this, and our constant, or our ratio here, is a ratio of 7. Then right here, you see that it's linear, and we have a constant of 4, or slope of 4. Right here, we can tell it's linear again, with a slope of -9. Right here, we can tell it's exponential, and it has a slope of 2/5 from right here. For number 13, this one looks a bit tricky, but it's linear. And even when you move this to the other side, you can see that it has that slope of -5. Or actually, yeah, no, slope of -5. It almost got me as well. 14, exponential. And it has that slope of 3 points. Don't know what that blue dot is, but we're gonna ignore it. 15, also exponential. this ratio of 2. Don't know why I keep writing ration. I think I'm a bit hungry today. I can't seem to erase it. And then for 16, you can add the 6 to the other side to make you more comfortable, but it's linear and has that slope of 3. Yeah, that was a speed run. Also, number 12, I wrote slope. It's actually ratio. I apologize. But make sure you don't mess that up because that can mean 2 different things. Ratio is when you're talking about exponential functions versus slope is when you're talking about linear. So make sure you fix that. Okay, now here we're actually going to be writing the equation for linear functions. So for number 17, our 2 given coordinates are 1, 4, and 3, 10. And the equation for slope, or the formula for slope, is y2 minus y1 over x2 minus x1. So here we can think of our y2 as 10 and our y1 as 4. So 10 minus 4 over 3 minus 1. You could also do this the other way around, 1 minus 10, but then you'd have to do, sorry, not 1 minus 10, 4 minus 10, but then you'd have to do 1 minus 3, so that's proportional. So 10 minus 4 is 6, 3 minus 1 is 2, so our slope is 3. So now we're going to put it in our format, which is y minus y1 equals our slope times x minus x1. So y minus, let's say we're using this coordinate, y minus 10 equals our slope, which is 3, times x minus 3 over here. You could also write it where the 10 is on the other side, so like x plus 10, or you can use the other coordinate, so y, sorry this is a bit messy, y minus 4 equals 3 times x minus 1. Either would be correct. For number 18, let's say our y2 is 3 and our y1 is 15. So 3 minus 15 over 10 minus 4. So negative 12 over 6, which is negative 2. So that's our slope. So let's say we're using this coordinate pair, y minus 3 equals negative 2 times x minus 10. You could also rewrite that as y equals negative 2 x minus 10 plus 3 if you want to move this to the other side. Or use the other coordinate pair, so y minus 15 equals negative 2 times x minus 4. But it's up to you. Then right here, 5 minus 2 over 13 minus 10 is equal to 3 over 3, which is just 1. So that's our slope. So let's say we're using this coordinate pair this time. Y minus 2 equals, you don't have to include the 1 there, but if you want to, 1 times x minus 10. Or you can rewrite it as y equals 1 times x minus 10 plus 2, if you want to move this over. Okay, now we're doing the same thing except for exponential functions. So here, again, let's remember y equals a times our ratio to the power of x. So our x is changing by 2, and let's say our y is 10 here, and our initial value, which is a, is 4. So we can input that into our function, or our formula. So 10, our y, equals our initial value, which is 4, times our ratio, which we don't know yet, to the power of 2, since we're changing by 2 right here. So now we can solve for our ratio. We can divide by r, so 10 over 4 equals r squared. And to get rid of this power, we can just square root both sides. So r equals the square root of 10 over 4. So now we just have to go back and write our final equation. So y equals our initial value, which in this case is 4, times the square root of 10 over 4 power of x minus 1, since that's our x value right there. Or you could write it as y equals 10 times the square root of 10 over 4 to the power of x minus 3. Again, like we talked about earlier, it just depends on which coordinate you want to focus on, but either of these would be acceptable. Now for this one, same thing, just remember our formula, y equals ar to the power of x. To solve for r, we want to plug in our values. So let's say our y is 3, our initial is 15. 3 equals 15 times r to the power of 6. Since from 4 to 10, we're going up by 6. So now we can solve. Divide by 15. So 3 over 15 can also be simplified to 1/5 equals r to the power of 6. And then you want to find the 6th root of 1/5. I know it looks a bit silly, but r equals 6th root of 1/5. So now we can go back and write our final equation. Y equals our initial value, which here is 15, times the 6th root of 1/5 to the power of x minus 4. You could also write y equals 3 times 6th root of 1/5, but it'd be to the power of x minus 10. So just make sure you're correlating them and not just writing wherever. But yeah, either of those would also be acceptable. Okay, now for the last one, we can see, let's say our initial was 2 and our final y was 5. So remember our formula, y equals ar to the power of x. So 5 equals our initial, which here is 2, to the power of our ratio, or times our ratio, which we don't know yet, to the power of, let's see, here we can see our x is increasing by 3, so 2r cubed. So now to solve for our ratio, we can divide by 2 on both sides, so 5 over 2 equals r cubed. Then we can take the cubed root of each side, so r equals the cubed root of 5/2. Now we can plug it back into our final equation, so y equals 2 times the cubed root of 5/2 times x minus 10. Or you can write that as y equals 5 times the cubed root of 5/2 times x minus 13. Both would be right. And that'll be the end of our lesson today. I apologize if I sound a bit stuffy, but I am getting over a cold. As always, I will be putting all the practice that we did today in the comments as well as the answer key so you can check your work. So get studying, and happy early holidays. As you can see, my Christmas tree is already up. But yep, good luck.